In general, in the acoustics testing or sound testing, you can commonly hear like three terms. One is called as sound pressure, then the other is sound power, and there is sound intensity. Let's take a look at that and see what are the differences and what are the benefits or shortcomings. So if you have a sound source like the one shown in the left-hand side in the picture, there is a source which is making a noise. It's in a room. The total amount of sound energy that is coming from that source, that can be quantified in terms of the sound power. At different operating conditions, perhaps they will generate different amounts of sound energy, and so the sound power will be different. And this sound power is a characteristic of the source. So no matter what the environment you are in, that doesn't play much of a role in terms of how much the sound power is generated. It is purely characteristic of the source. So that is the sound power. Then there is sound pressure, which is the result of the sound generated from a source. So we can measure the sound pressure using as a microphone, for example. And this is the sound power is the cause, and the sound pressure is the result of that, is the effect of that. As you move the microphone at different locations away from the source, we can see that the sound pressure will change, and it is very much dependent on the environment you are measuring in. So if it is a quiet environment, like no background noise, then sound pressure will be one thing. If you are having the same sound source in a noisy environment, then the sound pressure will be different. This sound power and sound pressure are analogous to like a heat source in a room, right, which is shown in the bottom right-hand side picture here. So if there is a heat source in a room, like a heater, the total amount of heat energy that is radiated from it, it's quantified in terms of watts, right, power or watts. The temperature in a room will be dependent on where you are measuring. Are you measuring close to the source or further away from the source? And the temperature is similar to sound pressure. So it is very much dependent on where you are measuring and the environment you are measuring, whereas sound power is similar to the total power or the total heat energy radiated from a source. So they are analogous in terms of the way they behave. So here, in terms of the units, if you look at it, just like the heat energy, which is measured in terms of the power in terms of the watt, the sound power is also is shown in watts, okay, and it is represented by uppercase P. The sound pressure, you are measuring like pressure, and the unit for that is pascals, and it is typically shown with lowercase p. So even in this presentation, you will see that the lowercase p is typically consistently in terms of the sound pressure, and the uppercase P is the sound power. So sound pressure and sound power. So let's take a look at the sound intensity. Sound intensity, it is a vector quantity, and it shows how much amount of sound energy or acoustic energy is flowing through a unit area. So sound power is a total energy radiated from the entire source, whereas sound intensity is the amount of acoustic energy radiated that flows through a unit area, like through a small area. Intensity is calculated by measuring the sound pressure, which is the lowercase p here, and then times the particle velocity. That is the velocity of the particle in the air at that location. So you have the pressure multiplied with the particle velocity, and that the product of those two gives the intensity. And the unit for the intensity is the sound power divided by the meter square, so that is watt per meter square. And this P is the sound pressure. That is the same sound pressure that we saw previously, the lowercase p. And the particle velocity, it is a vector quantity. So sound pressure is scalar, but the particle velocity is vector, and so sound intensity is also a vector quantity. And that is one of the unique aspects of sound intensity. It is that it is a vector, and so you know the direction in which the sound is coming, and that helps us greatly in terms of localization. What are the hotspots on a source? As we were just discussing, sound pressure is a scalar quantity, and so we don't know exactly what the direction in which the sound is flowing, but sound intensity is a vector, so that's why it helps us to localize the sources. One other advantage of intensity is that it can be measured in any sound fields. That means even if there is background noise, you're still able to measure the intensity. we will take a look at an example of that shortly. Intensity being a vector quantity, that really does help us to remove the effect of the background noise. So let's now take a look at how to go from intensity to the sound power. So suppose you have a sound source like shown by this red circle, which has a sound power of P, and let's say it's a point source, so it is radiating sound uniformly across all directions. So the sound intensity at a particular distance will be, intensity is the sound power divided by the surface area over for that radius. So suppose you have this R1, which is a smaller distance to the source, and then R2, which is the larger distance to the source. You get the sound power by measuring the intensity at certain distance on the surface of the sphere, and you sum up all the intensities multiplied with the corresponding areas over which it has been measured. So even though here you can see that one measurement, like the I1 measurement, is made measured close to the source, and then the I2 measurement is made further away from the source. When you take the intensity, measured intensity, multiplied with the area and sum up them over the entire sphere, you will see that the total amount of sound power will still be the same. So when you increase the radius for the second is 2 times that, the intensity values correspondingly reduces, such that the product of the intensity with the area will give you the total sound power, which will be the same for both cases. So to compute the sound power from intensity, you measure intensity at different locations and multiply that intensity with the corresponding area over which it is measured, and sum them over all the intensity measurement on that surfaces to come up with the total sound power. Next, let's take a look at the example of the background influence of the background noise. So as I said, one advantage of the intensity measurement is that you can do measurements in situ. So that means that even if there is presence of background noise, still you are able to do the intensity measurement to compute the sound power.
So I don't need a noise room.
Pardon?
I don't need a noise room.
That's a huge advantage, right? So what that means is that you don't necessarily have to perform the measurements in a semi-anechoic or an anechoic chamber. You can perform the measurement like in a factory kind of a setting, right?
Perfect.
Where there's a lot of background noise. That's a big deal. And why does that happen? That's because intensity is a vector quantity. So suppose you have a sound source which has a certain sound power, and you're trying to measure its sound power. You measure along its surface, and you can see that when you sum up the measured intensity with the corresponding areas, you get the total sound power. In this left-hand side case, you will see that the measured area covers the sound source. If on the other hand, you have the source which is outside, so let's say like the influence of the background noise, and you measured the intensity over the area which is affected by that background noise, you see that some amount of sound energy comes in, some goes out. And because it's a vector quantity, and then when you sum up together, you will see that the total will be 0 in this case on the right hand side. So that is one great advantage of this sound intensity measurement, is that you can determine sound power very reliably even in the presence of background noise. So let's see how to measure sound intensity. For measurement of intensity, we need 2 quantities. One is the sound pressure, and the other one is the particle velocity. You can get the particle velocity. There are some probes out there, like a microflowing probe, which measure particle velocity. When you do the intensity measurement, you directly get the intensity based on the sound pressure and the particle velocity. But they are many times delicate equipment to measure particle velocity. So most commonly, people use 2 microphones to measure the sound pressure, and those microphones are separated by a fixed spacer, and that spacer is the delta R. So here in this case, on the right hand side, you can see there is a probe, intensity probe, right? There are 2 microphones, one on the left, one on the right, and there is a spacer in between them. And that spacer distance is a known distance. So based on the measured pressure between the 2 microphones and the known distance, you can calculate the gradient of the pressure change, which gives you an estimate for the particle velocity. And so ultimately you can compute the sound intensity based on the measured sound pressures, the P, the average of the 2 sound pressures, and based on the difference in the pressure measured at the 2 locations, and that gives you the particle velocity. So this is the formulation for calculating the sound intensity in the time domain. If you do the FFT of that, and you can get the transformation in frequency domain, and that is that is given on the right hand side. So intensity in terms of frequency is imaginary part of the crossbar spectrum divided by the angular frequency in radian per second. This delta R is the spacer distance or the spacer size, and that is a fixed known distance between the two microphones that has to be known. And you will see that there are different lengths of the spacers that are available. The spacer can be from going from 6 millimeter all the way to 50 millimeter or even more. And they have certain frequency limitation. So when you use a 6 millimeter spacer, you can get frequencies from about 250 hertz to maybe 10K. So the spacer distance determines the higher frequency limit. So as you increase in the size of the spacer, you can see that you can go lower in frequencies, but the upper frequency limits changes also. Based on your frequency range of interest, you will have to select a spacer that is appropriate for your application. It is also possible to use two different lengths of spacers and then combine the two sets of measurement to cover the entire frequency range that is of interest.
Just to add on that point by Raj, that spacer is due to wavelength. So as I go lower in frequency, my wavelength is longer. Yep. So I need more space between the microphones to capture that larger wavelength that would correspond to a lower frequency. And the converse is true for higher frequency. I would need a smaller spacer to capture that shorter wavelength appropriately for the higher frequencies.
Okay, next let's take a look at how to do the intensity measures. There are different techniques available to do this intensity measurement. So one is called as a discrete point method, and the next one is called as a scanning method. In a discrete point method, you divide the surface area that is of interest to you into smaller areas, and you use the intensity probe to measure the intensity in these smaller areas or this discrete location. So when you have a sound source, you build an imaginary surface around that to cover all the sides of that. It can be in terms of parallelepiped, or it can be in the hemisphere or a center, and you break down the whole surface area into smaller areas. In this case, on the bottom left hand side, you can see that the parallelepiped, each face of that parallelepiped is broken down into smaller areas, like 4 areas, and the source is within that area, within the parallelepiped. That is called as a discrete point method. On the other hand, if you, rather than measuring at discrete points, you can do a scan as well, right? In a particular face or a surface, you can do a scan. You can do a scan like horizontally or vertically. So both of these methods are available. The discrete point method depends on the number of points you select. It can take a longer time to do that, but the advantage of the discrete point method is that you know exactly where the noise is coming from. So it may take longer to do it, but because you are measuring intensity at each of the locations, you will know where is the noise coming out, which is maximum. If you look at these 4 points here, it may be possible that the top left-hand side is the highest sound. So that gives an idea that something close to that will be the maximum noise generator. Whereas when you do the intensity using the scanning method, you don't have that.
So both methods are good for the sound power calculation, but the benefit for me doing more points, although the negative is it can take me more time and I have to do more measurements.
Yep.
The benefit is I'm going to get higher resolution in any kind of source localization.
Correct.
Result. Okay.
Excellent. Yep. Now, the other advantage of the intensity-based measurements is that there are some data validation tools that help you determine whether the data that you have collected is good data or not. There are some standards like the ISO 9614 standard that help you determine that. The ISO 9614 standard is for the determination of sound power based on sound intensity measurement. Similarly, you can do the sound power measurement based on sound pressure, which is the ISO 3744 or 45 standard. But for the intensity based one, it is ISO 9614. So if you measure the intensity and you want to know, hey, whether my measurements, the data quality is good or not, these validation tools will help you determine that. For example, like, when you do the measurements, you don't know how many points to measure. Like, what is the size of the area of each of the smaller areas that you're going to measure in the discrete point method. You don't know that beforehand, but these validation tools will help you determine that. And there are some corrective actions that are recommended based on the measurements you make, which guide you in terms of, hey, I made or 5 or 6 measurement points in each surface. Maybe that is not enough. One other thing is that these validation tools, they are called as field indicators, and they're available for both the 9614-1 standard, which is the discrete point method, and also the 9614-2, which is for the scanning method. So there are the field indicators F1, F2, F3, F4. So those field indicators are evaluated on each octave band or each 1/3 octave band, and they tell you whether there are enough number of points that you have measured, and also what is the size of the area that you have to measure. Like, if you have a source and you are measuring around that source, and like the imaginary surface area that you are going to measure, what should be its dimension. Those will come as a result of doing these quality checks in terms of the validation tools. Within test lab, there is implementation to help you to determine that.